From Earth it looks like a cosmic hat, the Sombrero Galaxy dazzling with mystery. But behind its brilliant glow it hides secrets about how galaxies form and evolve. What makes this galaxy so unusual? Together we'll explore its hidden story. If you enjoy, please like, subscribe and share, and drop a comment. What do you think this galaxy is hiding? Thank you for watching. Now let's begin. The Sombrero Galaxy rests in the southern reaches of the constellation Virgo, just below the celestial equator where it can be observed by telescopes in both hemispheres of Earth. In the night sky, it appears faint to the unaided eye, but in medium and large telescopes, its form reveals a bright core bisected by a dark lane. Early astronomers noted its unusual outline. Charles Messier in the 18th century compiled a catalogue of fuzzy objects that could be mistaken for comets. In that list, now called the Messier catalogue, the Sombrero Galaxy is included as Messier number 104. It is among the brighter galaxies visible from Earth, but its unusual shape, narrow plane, and strong central light make it stand apart. Observers in the 19th century using larger refractors and reflectors remarked on the distinctive dust band cutting across the middle of the bright oval. The galaxy earned descriptive nicknames from its appearance, yet its scientific study remained limited until the 20th century, when photographic plate spectroscopy and eventually space-based observatories became available. Locating the galaxy in the sky requires precise coordinates. Its right ascension is near 12 hours, and its declination near -12 degrees. These numbers place it within the expanse of Virgo, a constellation rich in galaxies due to the Virgo cluster and nearby structures. Despite this association, the Sombrero Galaxy is not a true member of the central Virgo cluster. Instead, it lies in the foreground at a distance that is significant but still closer than the dense cluster core. Amateur astronomers searching for it today often scan the region just west of the bright star speaker, using star charts or electronic guidance to refine the view. When seen in long exposure images, the galaxy stands out clearly, its central bulge bright and its dust lane crisp, but in direct eyepiece views, it is subtler with the dark band hinted at under steady skies. The observing history of the galaxy illustrates how astronomical progress has unfolded. In the era of Messier, the main task was to catalogue non-stellar patches of light to prevent confusion with comets. The entry for Messier 104 is brief, noting its faint round glow. By the time William Herschel and other 19th century observers studied it with larger instruments, more detail emerged. Herschel described the dark strip an unusual feature compared to the smooth haze of other nebulae known at the time. In the early 20th century, photographic techniques allowed the shape to be fixed permanently on plates. These plates confirmed the dark dust lane was not an artifact of the eye, but a real structural element of the system. Later, when Edwin Hubble and his colleagues established galaxies as separate island universes beyond the Milky Way, the Sombrero Galaxy became one of the striking examples of an external system with a peculiar form. Modern observatories offer multiple ways of viewing. Optical images reveal the bulge disk and dust lane. Infrared images penetrate the dust to show stars hidden from visible light. Radio observations map the gas distributed along the lane and disk. X-ray telescopes record hot energetic regions near the central nucleus. Each wavelength contributes a part of the overall understanding. Together they present a complex system whose brightness makes it an attractive target for detailed surveys. The Hubble Space Telescope has provided some of the most famous views, highlighting the sharpness of the central bulge and the symmetry of the dust band. These images are not only visually striking but also scientifically useful, allowing measurements of stellar populations and the structure of the central region. For astronomers, the significance of the Sombrero Galaxy lies not only in its appearance, but in what it reveals about galaxy structure in general. By being oriented nearly edge on it, offers a direct look at how a galactic disk appears when the line of sight passes through its plane. The dust lane becomes obvious, showing how interstellar material absorbs and scatters light. The bulge seen directly gives an impression of the distribution of older stars. Observers compare it with other edge-on galaxies to understand how disks, bulges and halos combine in different systems. The Sombrero Galaxy is among the brightest examples of this type, making it especially useful for study. The name most often used, Sombrero Galaxy, comes from its likeness to a wide-brimmed hat. While this description is common in scientific writing, the formal designation Messier 104 or NGC 4594 is employed. NGC refers to the New General Catalogue compiled in the 19th century, where it also appears. Catalogue numbers remain the stable identifiers across different observing campaigns and instruments. Researchers studying spectra star counts, or X-ray emission, refer to it by these identifiers to avoid ambiguity. Thus, while its appearance may inspire descriptive nicknames, the systematic designations ensure clarity across the scientific community. Its place in the Messier catalogue is also significant for historical reasons. Messier's list was never intended to classify galaxies as independent structures, since at the time the true nature of nebulae was not known. Yet many of the most famous galaxies were first widely documented in that list. For modern astronomy, the catalogue serves as a bridge between visual era observing and present scientific study. Messier 104 is among the more prominent entries because of its easily recognizable shape and brightness. Each year, amateur astronomers perform Messier marathons attempting to view all the catalogued objects in a single night, and the Sombrero Galaxy is one of the highlights of such events. Even with simple backyard telescopes under dark skies, the galaxy can be glimpsed as a small elongated patch. Larger amateur instruments show the dust lane as a shadow bisecting the oval. With professional instruments, details of the central bulge and faint outer halo emerge. Deep long exposures show faint structures beyond the obvious disk, including a rich system of globular clusters orbiting in the halo. These discoveries have shaped the modern view of the galaxy as unusually massive and complex compared with many galaxies of similar apparent size. In all, the Sombrero Galaxy's discovery and observing history demonstrate how gradual accumulation of data leads from mere description to deeper scientific understanding. From a faint blur noted to prevent comet confusion, it has become a well-studied system yielding insights into the structure of bulges, disks, halos, and dust. Each improvement in technology, from visual sketches to digital detectors, has added clarity. Astronomers continue to use it as a benchmark for studies of galactic morphology. It remains one of the most photographed and analysed galaxies outside the local group, not for dramatic reasons, but because its orientation, brightness and structure make it a convenient laboratory for observation. When the Sombrero Galaxy is examined in detail, its edge-on structure becomes the most striking feature. Seen almost sideways from Earth, the galaxy presents a thin disk cut sharply by a dark dust lane. Above and below that lane, a broad, luminous bulge dominates, filled with countless stars whose combined light overwhelms the surrounding sky. The contrast between the glowing bulge and the dark stripe of dust makes the system one of the clearest demonstrations of how interstellar material alters the view of a galaxy. The bulge itself rises steeply, forming a rounded glow that extends far from the disk. Unlike the thin and fragile appearance of the disk, the bulge appears concentrated and smooth, suggesting it contains many older stars bound together in a spherical distribution. The disk in comparison is razor thin when seen edge on its outline narrow against the sky, with the dust lane tracing its inner rim. This geometry is rare in nearby bright galaxies, making the Sombrero Galaxy valuable for study. The dust lane defines much of what can be learned about the galaxy's interior. Dust grains mixed with cold gas block visible light, leaving a shadow across the central bulge. In long exposures, the lane is seen to curve slightly around the bulge, forming a ring-like structure that circles the galaxy. Infrared images show the stars hidden by the dust, demonstrating that the obscuration is due to intervening material rather than a lack of stars. Radio maps of molecular gas further confirm the presence of large reserves of hydrogen and carbon monoxide concentrated in this ring. The combination of optical shadows, infrared starlight, and radio emission builds a coherent picture. The disk contains significant amounts of cold, interstellar material organized in a nearly circular band around the central bulge. The scale of the central bulge is extraordinary. Compared with galaxies of similar overall brightness, the bulge of the Sombrero Galaxy is unusually large. Its light dominates over that of the disk, giving the galaxy a profile more similar to an elliptical system. This contrast is one of the reasons that astronomers debate its classification, since spiral galaxies usually show stronger disk features, while lenticular galaxies show stronger bulges. The Sombrero Galaxy sits between these categories, with a bulge-to-disk ratio higher than most spirals, but with a disk still visible and containing interstellar matter. This balance makes it an important case for understanding transitional forms between spirals and lenticulars. The thinness of the disk also carries information. In edge-on galaxies, the thickness of the disk reflects the velocity dispersion of stars and gas. A thin disk indicates that most stars orbit in nearly the same plane with little vertical motion. The Sombrero Galaxy shows such a thin disk, suggesting a well-ordered rotation and relatively stable history without major disruptive events in the recent past. At the same time, the dust lane stands out with unusual clarity, meaning the disk is not only thin, but also filled with a coherent structure of dust and gas concentrated in a narrow region. These observations point to a system that, despite its massive bulge, maintains a disk that resembles those of more typical spirals. The bulge's surface brightness is so intense that it saturates photographic plates and digital detectors in long exposures. Astronomers use careful processing to separate the bulge light from the disk. By modeling the brightness profile, they show that the bulge follows a steep curve consistent with the profiles of elliptical galaxies. In contrast, the disk follows an exponential profile typical of spiral disks. This combination emphasizes the hybrid nature of the system. The dust lane cutting across the bulge reinforces the impression of two components, superposed a nearly elliptical bulge, and a thin spiral-like disk intersecting it. Observing the galaxy in different wavelengths provides a more complete view of these structures. In visible light, the contrast is sharp, with the dust lane black against the white bulge. In near-infrared, the dust is partly transparent, revealing stars embedded within the lane. In far-infrared and sub-millimeter wavelengths, the dust itself glows faintly, allowing measurements of its mass and temperature. These observations show that the dust is relatively cool, only a few tens of degrees above absolute zero, but massive enough to obscure vast regions of starlight. In radio observations, the gas associated with the dust lane is mapped, confirming that it is concentrated in a rotating ring. Together, these results show the galaxy not just as a static form, but as a system, with active interstellar matter shaping its appearance. The structural orientation also aids in understanding the three-dimensional arrangement. Because the galaxy is viewed edge-on, astronomers can measure the vertical distribution of stars and dust more easily than in a face-on system. By tracing the dimming of starlight through the dust lane, they calculate the thickness of the absorbing layer. By measuring the brightness of stars above and below the lane, they estimate the shape of the bulge. These direct geometric studies are difficult in galaxies seen at other angles, where projection effects complicate the measurements. Thus, the Sombrero Galaxy offers a natural laboratory for testing models of bulge and disk structures. The outer regions of the disk, though faint, extend well beyond the central bulge. Deep images show a halo of starlight surrounding the galaxy with faint streams of stars possibly connected to past accretion events. Yet the main visible features remain the bulge disk and dust lane, each clearly defined in the edge on view. Observers often remark that the simplicity of this geometry allows a clearer understanding of galactic components than in more complex face on spirals, where arms, bars, and irregular features blend together. In the Sombrero Galaxy, the major parts are set side by side with the bulge dominating the disk cutting across, and the dust lane marking the presence of interstellar matter. For scientific study, these features provide essential clues to the formation and evolution of the galaxy. The large bulge suggests an early rapid assembly or mergers, while the thin disk and coherent dust lane suggest long-term stability afterward. The rich globular cluster system observed in the halo adds further weight to the interpretation of a massive early history. Each structural element contributes a piece of evidence, and the edge-on orientation presents them with unusual clarity. The Sombrero Galaxy thus serves not only as a striking image, but as a key object in the study of galaxy morphology and structure. Astronomers classify galaxies to better understand how they form and evolve, yet the Sombrero Galaxy challenges simple placement within standard schemes. The most common classification systems, such as the Hubble sequence, arrange galaxies from ellipticals through lenticulars to spirals. Spirals have distinct arms, visible disks with dust and gas, and often strong star formation. Lenticulars labelled S0 bridge the gap between spirals and ellipticals, showing disks, but lacking obvious arms and exhibiting more dominant bulges. When the Sombrero Galaxy is examined, it reveals properties of both categories, which explains the long-standing debate over how to describe it. In optical photographs, the dark dust lane, the thin disk, and the presence of interstellar gas point toward a spiral nature. These features are typical of spirals where cold gas accumulates in disks and forms stars. However, the overwhelming brightness and size of the central bulge resemble those of lenticular or even elliptical galaxies. The bulge-to-disk ratio is unusually high for a spiral, meaning that the bulge contains far more light and mass than the disk does. As a result, some researchers describe the Sombrero Galaxy as a borderline case not fitting comfortably into one category. The lack of clear spiral arms complicates matters further. In face-on spirals, arms trace regions of star formation, but in the edge on view of the Sombrero Galaxy, arms will be difficult to detect even if they were present. Despite deep imaging, no obvious spiral pattern has been confirmed. Instead, the disk appears smooth, with the dust lane forming the most prominent structure. This smoothness supports a lenticular classification, since lenticular galaxies often lack defined arms. Still, the presence of cold gas and dust unusual for lenticulars resists a simple conclusion. Spectroscopic studies add to the evidence. Measurements of the motions of stars in the bulge show random velocities characteristic of spheroidal systems. In contrast, measurements in the disk reveal ordered rotation around the galaxy's center, as expected in spiral disks. The combination of random bulge motion and organized disk rotation again shows hybrid features. Researchers attempting to assign a single label have alternated between spiral and lenticular depending on which property they emphasize. Some catalogues list it as type SAEA, an unbarred spiral with tightly wound arms, while others list it as S0A lenticular. Understanding the classification debate requires recognizing that categories are human constructs applied to natural systems that may not follow strict boundaries. The Sombrero Galaxy illustrates this by occupying a middle ground. Its bulge resembles an elliptical in brightness, and scale its disk resembles a spiral in thinness and structure, and its dust and gas content signal active interstellar processes not common in lenticulars. Rather than a problem, this ambiguity provides an opportunity to study transitional forms. Galaxies may evolve from one type to another through mergers, accretion, or internal processes, and objects like the Sombrero Galaxy offer insight into these transitions. Another factor in the debate is the unusually rich system of globular clusters surrounding the galaxy. The number of these old star clusters is far higher than in typical spirals and more consistent with giant ellipticals. This richness supports the view that the galaxy is massive and early forming, with a bulge assembled in the distant past. At the same time, the existence of an ordered disk with gas suggests that the system retained or acquired material later to form a spiral-like component. Thus, the classification dispute reflects real complexity in the galaxy's history rather than simple disagreement. When viewed across different wavelengths, the picture remains mixed. In infrared light, the bulge dominates even more, strongly reinforcing the impression of a lenticular or elliptical type. In radio wavelengths, gas and dust reveal a structure more characteristic of spirals. X-ray data from the central region show signs of a low-luminosity active nucleus, a feature that can appear in many galaxy types. Each observation emphasizes different traits, keeping the classification ambiguous. Some astronomers argue that the traditional categories may not capture the full diversity of galaxies in the universe. They suggest that galaxies like the Sombrero highlight the need for continuous rather than discrete classifications. Instead of fitting every galaxy into a single box, researchers may describe them by multiple parameters such as bulge size, disk, thickness, gas content, and star formation rate. Under such a multi-dimensional system, the Sombrero Galaxy would occupy an extreme region with a large bulge, a thin disk, significant dust, and moderate star formation. This approach reduces the tension of assigning one label while acknowledging the unique combination of properties. The classification debate is not merely academic because labels guide how models of galaxy formation are applied. If the Sombrero Galaxy is treated as a spiral, models must explain how it developed such a dominant bulge. If it is treated as a lenticular, models must explain why it retains so much dust and gas. Each perspective leads to different scenarios for its past evolution. By studying its ambiguous nature, astronomers refine models to allow more varied histories. In this way, the classification uncertainty becomes a useful tool rather than a hindrance. Educational resources often present the galaxy as a prime example of classification difficulty. Students learning about the Hubble sequence see it as a case that challenges strict definitions. It demonstrates that real galaxies can carry overlapping traits and that nature is not bound by human categories. For professional research, it serves as a reminder that detailed observations are required before assigning types, and that classifications must evolve with new data. The Sombrero Galaxy's mixed features continue to stimulate discussion in astronomical literature, showing that even well-known objects can resist simple description. Ultimately, the Sombrero Galaxy demonstrates that galaxy morphology is a spectrum rather than a set of boxes. Its bright bulge, thin disk, and heavy dust lane ensure that it cannot be easily confined to one category. By confronting this challenge, astronomers deepen their understanding of galactic diversity and the processes that shape galaxies over billions of years. Its very ambiguity is what makes it a key reference point for exploring how galaxies are grouped how they evolve, and how classification systems must remain flexible to accommodate complex realities revealed by careful observation. The light of the Sombrero Galaxy is dominated by its bulge, a dense collection of stars that contributes the majority of the galaxy's visible brightness. The bulge is a spheroidal structure rising above and below the disk, extending for many thousands of light years. In this region, stars are packed more closely together than in the disk, and their orbits are oriented in random directions rather than confined to a plane. This random motion produces the smooth, rounded glow observed through telescopes. The overwhelming contribution of the bulge to the total luminosity makes the Sombrero Galaxy unusual, compared with most spirals where the disk often plays a more prominent role in producing light. The bulge of the Sombrero Galaxy resembles that of giant elliptical galaxies, which are dominated entirely by such spheroidal stellar distributions. The stars in the bulge are generally older and redder than those in the disk. Observations show that these stars are metal-rich, meaning that they contain higher proportions of elements heavier than helium, compared with stars that formed early in the history of the universe. Metals in astronomy include all such heavier elements, and their presence is a record of past generations of stars that lived and died, releasing material through winds and supernovae. The concentration of metal-rich stars in the bulge indicates a long history of star formation and enrichment that took place billions of years ago. The overall colour of the bulge reflects this older population, with less blue light from young stars and more reddish light from evolved stars such as red giants. In contrast, the disk contains a wider range of stellar populations. Embedded within the disk are younger, hotter, bluer stars that formed from the interstellar gas present in the dust lane and surrounding ring. These younger stars provide a trace of ongoing star formation, even though the galaxy is not in a major starburst phase. The mixture of populations highlights the difference between bulge and disk. The bulge preserves the record of early star formation and enrichment, while the disk reflects more recent activity. In edge-on view, the bright bulge outshines much of the disk, but careful photometric analysis allows astronomers to separate the contributions. Halo stars add another layer to the population. The halo is a vast faint region surrounding the galaxy populated by old stars and globular clusters. The halo stars are generally more metal-poor than those in the bulge or disk, meaning they formed earlier in the universe before multiple cycles of enrichment had occurred. These halo populations provide insight into the earliest phases of the galaxy's formation, when smaller fragments merged and left behind relic stars in wide orbits. In the Sombrero Galaxy, the halo is especially rich in globular clusters, far more than the Milky Way contains. These clusters are dense spherical groups of old stars bound tightly by gravity, and they represent some of the oldest surviving structures in any galaxy. By studying the different populations, metal-rich bulge stars, mixed-age disk stars, and metal-poor halo stars, astronomers reconstruct the sequence of events that built the galaxy. The dominance of the bulge suggests that a major phase of star formation and mass assembly took place early. The presence of a thin disk with ongoing star formation suggests that gas was retained or accreted later to maintain more recent stellar birth. The halo and its globular clusters point to ancient building blocks that merged to form the main body. Each component tells a piece of the history, and together they create a layered record spanning billions of years. Spectroscopic studies reveal details about individual stars and clusters within the galaxy. By dispersing the light into spectra, astronomers measure chemical abundances, velocities, and ages. The bulge spectra show strong metal lines confirming enrichment. The disk spectra show a mix of features from young and old populations, indicating continuous star formation over time. The halo spectra show weaker metal lines confirming the ancient origin of those stars. Velocities measured through the Doppler effect show that bulge stars move randomly in all directions, while disk stars rotate coherently around the center, and halo stars follow elongated orbits reaching far from the core. The central bulge also hosts many evolved stars at late stages of their life cycles. These include red giants and horizontal branch stars, which serve as distance indicators through techniques like surface brightness fluctuations. By analyzing how the brightness of the bulge fluctuates due to statistical variations in star counts, astronomers estimate the distance to the galaxy. Thus, the stellar populations not only reveal history, but also serve as tools for measurement. Globular clusters surrounding the Sombrero Galaxy are of particular interest. Estimates suggest the galaxy may contain nearly 2,000 such clusters, compared with about 150 in the Milky Way. Each cluster contains hundreds of thousands of old stars tightly packed into a sphere only a few tens of light years across. The abundance of clusters implies that the galaxy is extremely massive, since the number of globular clusters tends to scale with the total mass of the host galaxy. These clusters orbit far into the halo, forming a swarm around the bulge and disk. They provide further evidence that the Sombrero Galaxy assembled rapidly and early, collecting enough material to form a vast system of clusters. The study of stellar populations in the Sombrero Galaxy therefore yields a detailed portrait of its structure and evolution. The bulge is bright, massive, and metal-rich, dominated by old stars but enriched by multiple generations of stellar birth and death. The disk is thin-ordered and home to younger stars forming from interstellar gas. The halo is extended faint and populated by ancient metal-poor stars and globular clusters. Each component fits together into a coherent model. An early intense phase of star formation created the bulge and halo, followed by a more extended, quieter phase that maintained the disk. The galaxy's present appearance reflects this layered history visible in the light of its stars. The Sombrero Galaxy is remarkable for its unusually rich population of globular clusters, far exceeding the numbers seen in most galaxies of similar size and brightness. Globular clusters are dense spherical groups of ancient stars bound tightly by gravity, often containing hundreds of thousands of members. These systems are among the oldest structures in the universe, having formed more than 10 billion years ago, and they act as fossil records of early galactic assembly. The Milky Way hosts roughly 150 such clusters, and even large spiral galaxies rarely contain more than a few hundred. In contrast, the Sombrero Galaxy is estimated to possess nearly 2,000 globular clusters, placing it closer to giant elliptical galaxies in this respect than to typical spirals. This extraordinary abundance suggests that the total mass of the Sombrero Galaxy is extremely high, and that its formation history included intense early episodes of star formation and mergers. The presence of so many globular clusters is not obvious in casual images, because individual clusters are faint and widely dispersed around the galaxy. Careful long-exposure studies, often using space-based telescopes like Hubble, have catalogued large numbers of these clusters in the halo. They appear as tiny points of light distinguishable from foreground stars by their colours and luminosities. Statistical methods confirm their identities, and spectroscopic observations measuring radial velocities prove that they are gravitationally bound to the Sombrero Galaxy. Mapping their distribution reveals a roughly spherical halo extending far beyond the bright disk and bulge, with clusters orbiting at distances of tens of thousands of light years. The sheer extent of this halo underlines the massive scale of the system. Globular clusters provide insight into the chemical evolution of the galaxy. Many clusters in the Sombrero Galaxy are metal poor, meaning that their stars lack heavy elements, and formed very early in cosmic history before repeated cycles of stellar enrichment. Others are more metal-rich, indicating formation, after some enrichment had occurred. The coexistence of both types suggests multiple formation epochs, perhaps tied to different stages of the galaxy's assembly. Metal-poor clusters may have formed in smaller proto-galactic fragments that merged to build the halo, while metal-rich clusters may have formed later in the central regions as the bulge and disk grew. The distribution of metallicities among the clusters provides a timeline for how the galaxy gathered its mass and developed its structure. The number of globular clusters is often correlated with the overall mass of the dark matter halo that surrounds a galaxy. Since dark matter dominates the gravitational potential, galaxies with larger halos can retain more material and form more clusters. The extraordinary cluster system of the Sombrero Galaxy therefore points to an unusually massive halo. This inference is supported by dynamical studies of the rotation curve, which show high velocities sustained far from the center, requiring a large amount of unseen matter. The globular cluster population is consistent with this conclusion, serving as independent evidence that the galaxy is massive on a scale rivaling much larger systems. The orbits of globular clusters also reveal information about the galaxy's past. Clusters move in elongated paths that carry them through the halo and around the bulge. By measuring their velocities, astronomers determine the mass distribution within the galaxy. The observed motions match the predictions of a heavy central concentration surrounded by a vast dark matter halo. Some clusters show peculiar velocities or unusual chemical compositions, suggesting that they may have originated in smaller galaxies later accreted by the Sombrero Galaxy. In this way, the cluster system records not only the early formation of the galaxy, but also its later interactions. Comparisons with the Milky Way highlight the unusual nature of the Sombrero's cluster population. The Milky Way's halo of 150 clusters is already considered rich, yet the Sombrero Galaxy contains more than 10 times that number. Even accounting for its brighter bulge and larger total mass, the excess is significant. It places the Sombrero Galaxy in the company of giant ellipticals like those found in galaxy clusters, which often possess thousands of clusters. The fact that such a system exists in a galaxy, with both a disk and dust lane, challenges simple categorizations and shows how diverse galaxy properties can be. Globular clusters are also useful as distance indicators. The brightest clusters have predictable luminosities, and by comparing their apparent brightness with their intrinsic brightness, astronomers estimate the distance to the host galaxy. In the case of the Sombrero Galaxy, studies of its cluster system have provided distance estimates consistent with other methods such as surface brightness fluctuations and the Tully-Fisher relation. The agreement among these methods strengthens confidence in the measured distance, which is around 30 million light-years. The clusters therefore serve both as historical records and as practical measuring tools. The richness of the cluster system influences how the Sombrero Galaxy is interpreted in the broader context of galaxy evolution. It suggests that the galaxy underwent a vigorous period of early star formation, capable of producing vast numbers of dense stellar systems. Such intensity may have been driven by rapid collapse of gas or by early mergers of protogalactic fragments. The subsequent survival of so many clusters indicates that the galaxy's gravitational field has remained strong and stable for billions of years, preventing disruption. This stability contrasts with smaller galaxies, where clusters can be lost or destroyed over time. Astronomers continue to study the cluster system in detail because it offers one of the clearest windows into the galaxy's ancient past. By analysing the ages, metallicities, and motions of individual clusters, they reconstruct the sequence of events that built the galaxy. Some clusters may have been captured from smaller galaxies, leaving signatures in their chemical compositions. Others may trace star formation bursts linked to the growth of the bulge. Each cluster is a time capsule preserving information from an era otherwise inaccessible. The vast number of clusters in the Sombrero Galaxy ensures that the statistical sample is large, providing robust conclusions about its history. The study of globular clusters also helps place the Sombrero Galaxy within the broader universe. Surveys of galaxies at greater distances show correlations between cluster populations and galaxy properties. By comparing the Sombrero's cluster system with those in other galaxies, astronomers test theories of galaxy assembly. The extreme richness of the Sombrero system marks it as an outlier among nearby spirals, raising questions about whether it followed a more intense evolutionary path, or whether it represents a common but under-recognized stage of development. Continued observations, especially with high-resolution instruments capable of resolving individual stars within clusters, aim to refine these comparisons. The halo of globular clusters surrounding the Sombrero Galaxy thus stands as one of its defining features. It confirms the galaxy's massive scale, provides tools for measuring distance records, the chemical and dynamical history, and challenges simple classification. The extraordinary abundance of clusters makes the Sombrero Galaxy an essential target for understanding how galaxies assemble and how ancient stellar systems survive over cosmic time. By tracing the light of these dense ancient groups, astronomers gain a clearer view of the earliest chapters of galactic evolution, preserved in the vast halo that envelops the bright bulge and thin disk of this striking system. The Sombrero Galaxy is not defined only by its bright bulge and swarm of globular clusters. It also contains significant amounts of gas and dust, arranged in a distinct ring that wraps around the disk. This ring appears as the dark band seen in optical images, where interstellar dust blocks and scatters starlight. When astronomers study the galaxy in other wavelengths, the role of this dust and the gas associated with it becomes clear. Infrared observations from instruments such as the Spitzer Space Telescope reveal the dust glowing faintly with its own emission, heated to only a few tens of degrees above absolute zero by the radiation of nearby stars. In these infrared images, the ring is bright, outlining a continuous circle of material surrounding the bulge. This confirms that the dark band in visible light is not an absence of stars, but rather a concentration of cold interstellar matter. Radio observations provide further detail by tracing gas that is invisible in optical light. Neutral hydrogen emits radio waves at a wavelength of 21 centimeters, allowing astronomers to map its distribution. In the Sombrero Galaxy, hydrogen gas is concentrated in the same ring as the dust, forming a coherent structure that orbits around the center. Molecular gas traced by the emission of carbon monoxide at millimeter wavelengths is also present, again concentrated in the ring. These gases provide the raw material for star formation. Their presence is somewhat surprising given the dominant bulge, since many bulge-dominated galaxies have lost most of their cold gas. The Sombrero Galaxy has retained or acquired enough material to maintain a significant interstellar medium. The structure of the ring is sharply defined. Unlike spiral galaxies with widespread dust lanes winding through arms, the Sombrero Galaxy shows a single dominant ring encircling the bulge. This arrangement makes it easier to study the properties of the interstellar medium without the confusion of multiple overlapping features. The ring is nearly circular, though slightly tilted relative to the plane of the disk. Its symmetry suggests that it has been stable for a long period, maintaining its form as the galaxy rotates. The dust within the ring absorbs a substantial fraction of the visible light, creating the sharp silhouette that gives the galaxy its distinctive appearance. Multi-wavelength studies reveal variations within the ring. Infrared images show clumps of dust where star formation is more active. Radio maps show concentrations of gas corresponding to these regions. Optical images reveal knots of young blue stars emerging in gaps where dust is less dense. Together, these observations demonstrate that the ring is not uniform but hosts localized sites of activity. These are the regions where gravity has caused gas clouds to collapse and form new stars. The surrounding dust both hides and protects these forming systems, while also making them visible in infrared light. The total mass of gas and dust in the Sombrero Galaxy is modest compared with large star-forming spirals, but significant for a system with such a dominant bulge. Estimates place the mass of neutral hydrogen at several billion solar masses, with molecular gas contributing additional billions. The dust itself makes up only a small fraction of this mass, but plays an outsized role by obscuring light and cooling gas to temperatures where stars can form. The ring therefore functions as the engine of ongoing star formation, even if the overall rate is lower than in more active galaxies. The interplay between the ring and the bulge provides clues to the galaxy's evolution. One possibility is that gas settled into the disk after the bulge had already formed, perhaps acquired through minor mergers or gradual accretion from the intergalactic medium. Another is that the ring is a long-lived remnant of the galaxy's original disk preserved, because the galaxy has avoided major disruptive events for billions of years. In either case, the survival of a coherent ring of dust and gas alongside such a massive bulge is unusual and challenges simple evolutionary models. The dust lane also offers a natural laboratory for studying the properties of interstellar dust itself. By measuring how much light is absorbed at different wavelengths, astronomers determine the size, distribution, and composition of dust grains. In the Sombrero Galaxy, the extinction curve resembles that of the Milky Way, implying similar grain properties composed of silicates, carbon compounds, and ices. This suggests that the processes of dust formation in stars and dust destruction in supernovae operate in similar ways across different galaxies. The abundance of dust in the Sombrero Galaxy shows that these processes have continued over long timescales, replenishing material even as stars evolve and die. In addition to cold gas and dust, the galaxy also contains warmer and hotter phases of interstellar matter. X-ray observations detect diffuse hot gas near the central regions, likely heated by supernovae and possibly by activity around the central black hole. Ultraviolet observations reveal regions where young stars emit, strongly indicating the presence of short-lived massive stars recently formed in the ring. These different phases of the interstellar medium coexist, interacting through shock waves, radiation, and gravity. The balance among them controls the rate of star formation and the appearance of the galaxy. The prominence of the ring across so many wavelengths has made the Sombrero Galaxy a target for numerous detailed studies. Astronomers use it to investigate how interstellar matter is distributed in bulge-dominated galaxies, how dust lanes influence the visibility of stellar populations, and how star formation can persist in systems not classified as classic spirals. Because the ring is seen edge on, its geometry is simple to interpret, allowing direct measurements of thickness, density, and opacity. These results feed into broader models of galactic structure and evolution. The ring of gas and dust is therefore a central element of the Sombrero Galaxy's identity. It defines its optical appearance, regulates its star formation, and preserves evidence of its evolutionary history. Without the ring, the galaxy might resemble a simple, lenticular or elliptical dominated by its bulge and halo. With the ring, it presents a composite system combining features of multiple galaxy types, The study of this structure continues to inform not only the understanding of the Sombrero Galaxy itself, but also the general knowledge of how interstellar matter shapes galaxies across the universe. Star formation in the Sombrero Galaxy is closely tied to the ring of dust and gas that circles its bulge. This ring provides the cold molecular clouds necessary for the birth of stars, and observations across multiple wavelengths show where this process is occurring. In optical images, small bright knots appear along the ring, some shining with the blue light of young stars, others glowing faintly from surrounding nebulae. In infrared images, these regions are more clearly visible as warm patches where dust is heated by newly formed stars. In radio maps of molecular gas, the same locations show concentrations of carbon monoxide, confirming that clouds are collapsing into dense cores. These combined observations build a consistent picture of moderate but persistent star formation occurring primarily within the ring. The overall rate of star formation in the Sombrero Galaxy is lower than in more active spiral galaxies. Estimates suggest a few solar masses of new stars are created each year compared with tens of solar masses in starburst systems like the Antennae galaxies. This lower rate is consistent with the limited supply of gas which, while significant, is not abundant enough to sustain rapid star formation on a large scale. The dominant bulge also influences the process because its strong gravitational potential stabilizes the disk, making it harder for large-scale instabilities to form. As a result, the Sombrero Galaxy avoids the dramatic bursts of star formation seen in interacting galaxies, instead sustaining a steadier, quieter mode. Within the ring, however, conditions vary. Some segments are rich in dense clouds and actively forming clusters of stars, while others are relatively quiescent. This patchiness is typical of galactic disks, where local processes such as spiral density, waves cloud collisions, or feedback from supernovae regulate activity. In the Sombrero Galaxy, the absence of prominent spiral arms means that local variations in gas density, rather than global patterns, set the pace. This leads to a more uneven distribution of star-forming regions, visible as scattered bright knots instead of continuous arms. The newly formed stars within the ring range from small red dwarfs to massive blue giants. The most massive stars live only a few million years before ending their lives as supernovae, injecting energy back into the surrounding medium. This feedback shapes the future of star formation, compressing nearby clouds in some cases and dispersing them in others. The cycle of collapse formation and feedback maintains a balance that keeps the overall star formation rate relatively steady. The evidence of supernova remnants observed in radio and X-ray wavelengths confirms that this cycle is ongoing, even though the global rate is modest. Star clusters also form within the ring. These groups of hundreds or thousands of stars emerge from collapsing gas clouds and remain bound for millions of years. Some survive much longer, eventually contributing to the population of open clusters scattered through the disk. In the Sombrero Galaxy, these clusters are harder to study directly because of distance, but space-based telescopes have resolved some of them as distinct objects. Their properties are consistent with cluster formation in other galaxies, showing that the same processes operate across different galactic environments. The balance between quiet and active phases of star formation in the Sombrero Galaxy illustrates how interstellar gas is consumed over time. If the ring were to lose its gas without replenishment, star formation would eventually decline to negligible levels, leaving the bulge as the dominant feature. The persistence of star-forming regions suggests that either the ring is massive enough to fuel activity for billions of years, or that the galaxy acquires fresh gas from small accretions or from its surroundings. This question remains under study, as understanding the gas supply is key to predicting the galaxy's long-term evolution. Measurements of star formation rates rely on multiple methods, each sensitive to different timescales. Ultraviolet light traces stars formed within the past 100 million years. Infrared emission from dust traces the heating by young stars and radio emission from hydrogen. Recombination lines traces ongoing formation in nebulae. When these methods are applied to the Sombrero Galaxy, they converge on a consistent picture of modest but steady star formation. The agreement across wavelengths strengthens confidence in the results, showing that despite the overwhelming bulge light, the activity within the ring is real and measurable. The interplay between star formation and the central bulge is of particular interest. The bulge contains older stars and little gas, while the ring contains younger stars and abundant gas. The contrast highlights the division of roles within the galaxy. The bulge preserves the past, while the ring sustains the present. Yet the two are not entirely separate, since gravitational forces connect them. The bulge influences the stability of the disk, and the energy from star formation in the ring may affect the central regions. This dynamic interaction shapes the overall structure and ensures that the Sombrero Galaxy continues to evolve even in its relatively quiet state. Astronomers also compare the Sombrero Galaxy's star formation with that of the Milky Way. The Milky Way forms stars at a rate of about 1 to 2 solar masses per year, while the Sombrero Galaxy's rate is slightly higher but confined to its ring. The Milky Way shows spiral arms with widespread star-forming regions, while the Sombrero Galaxy shows a more concentrated pattern. These differences reflect their structures. The Milky Way is a typical spiral with a moderate bulge, while the Sombrero Galaxy is bulge-dominated with a ring of activity. Such comparisons reveal the diversity of ways galaxies can maintain star formation, depending on their histories and structures. The regulation of star formation in the Sombrero Galaxy is therefore an outcome of both supply and stability. The supply comes from the cold gas concentrated in the ring, while stability comes from the massive bulge that prevents runaway collapse. The result is a galaxy that forms stars quietly without dramatic bursts, yet consistently enough to refresh its disk with younger populations. This balance makes the Sombrero Galaxy a valuable case for studying how galaxies sustain star formation outside of extreme environments. It demonstrates that even systems with large old bulges can host active interstellar processes if gas remains available in their disks. At the heart of the Sombrero Galaxy lies a massive central object that strongly influences its surroundings. Evidence from observations across the electromagnetic spectrum points to the presence of a supermassive black hole in the galaxy's core. The mass of this black hole is estimated to be on the order of several billion times that of the Sun, making it one of the more massive central objects known in nearby galaxies. The case for its existence is built from multiple lines of evidence. The first is the motion of stars close to the center. By measuring how their velocities increase as they approach the nucleus, astronomers infer the presence of a concentrated mass too large to be explained by normal stars or gas. The second is the detection of radiation at radio and X-ray wavelengths from the central region, consistent with low-level accretion onto a black hole. Together, these observations leave little doubt that a supermassive black hole resides at the center of the Sombrero Galaxy. Unlike the highly active nuclei of quasars or powerful radio galaxies, the nucleus of the Sombrero Galaxy is relatively faint. This makes it an example of a low-luminosity active galactic nucleus. Material falling toward the black hole produces radiation, but at a much lower level than in more energetic systems. One explanation is that the accretion rate is low, with little gas reaching the immediate surroundings of the black hole. Another is that the accretion process is radiatively inefficient, converting less of the infalling mass into light. Whatever the cause, the result is that the galaxy's central engine is quiet, detectable only with sensitive instruments. Radio observations show a compact source at the nucleus corresponding to synchrotron radiation, produced by electrons spiraling in magnetic fields near the black hole. X-ray telescopes detect emission from hot gas close to the accretion region. Ultraviolet observations reveal some variability in brightness, another sign of ongoing though limited activity. These signatures together confirm the presence of an active nucleus, even if its luminosity is modest. The Sombrero Galaxy therefore serves as an example of how supermassive black holes can exist without producing dramatic outbursts. The existence of such a massive black hole also fits into the broader pattern observed in galaxies. Studies show a correlation between the mass of the central black hole and the velocity dispersion of stars in the bulge known as the M-sigma relation. The Sombrero Galaxy, with its enormous bulge, is expected to host a very massive black hole, and the measured estimates confirm this prediction. This reinforces the idea that the growth of bulges and black holes are linked through processes in the early stages of galaxy formation. The black hole and the bulge appear to have grown together, each influencing the other, through gravitational and energetic feedback. Although the nucleus is quiet now, it may not always have been so. In earlier epochs, when gas supplies were more abundant, the black hole could have accreted material at higher rates, producing a brighter active nucleus. Signs of past activity may remain in the structure of the central region, though direct evidence is limited. Today, the black hole persists as a massive but largely dormant feature, shaping the dynamics of the inner bulge and occasionally revealing itself through weak emissions. The environment around the black hole is studied through stellar dynamics. Stars orbiting near the nucleus show high velocities that rise steeply toward the center, a signature of the central mass. By modeling these motions, astronomers place constraints on the black hole's mass. Such studies require high-resolution imaging and spectroscopy, often from the Hubble Space Telescope, or large ground-based observatories using adaptive optics. Results consistently indicate a black hole mass of several billion solar masses, making it comparable to those in giant elliptical galaxies, despite the Sombrero Galaxy's spiral or lenticular classification. The relatively low level of nuclear activity also has implications for the galaxy's interstellar medium. Without strong outflows or jets from the black hole, the surrounding gas in the ring and disk is not disrupted on large scales. This may partly explain why the galaxy retains its cold gas and continues to form stars at a moderate rate. In more active systems, energetic feedback from the nucleus can heat or expel gas, shutting down star formation. In the Sombrero Galaxy, the quiet nucleus allows the ring to persist relatively undisturbed. This balance between central mass and modest activity provides a laboratory for studying the coexistence of a massive black hole and ongoing star formation in the same galaxy. Comparisons with the Milky Way highlight both similarities and differences. The Milky Way also hosts a central black hole known as Sagittarius A with a mass of a few million solar masses. The Sombrero Galaxy's black hole is more than 1,000 times more massive, reflecting its larger bulge. Both nuclei are faint compared with luminous quasars, but the Sombrero's is still detectable at greater distances because of its scale. These comparisons help astronomers understand the range of black hole masses and accretion rates across different galaxy types. The study of the Sombrero Galaxy's nucleus continues with new instruments capable of higher resolution and sensitivity. Observations in the radio with arrays such as the Very Large Array and the Atacama Large Millimeter Array probe the immediate environment of the black hole. X-ray observatories such as Chandra reveal hot gas and variable emission near the core. Infrared observations trace the distribution of dust that may be feeding the nucleus. Each wavelength provides a different piece of the puzzle, and together they build a coherent picture of a massive central engine currently operating in a subdued state. The central massive object is therefore a crucial component of the Sombrero Galaxy's structure. It anchors the dynamics of the bulge, influences the stability of the disk, and fits into the larger framework of galaxy-black hole relations. Even though it is faint compared with the most luminous active nuclei in the universe, its mass and presence are undeniable. The Sombrero Galaxy shows that supermassive black holes are common features of large galaxies, and that their influence extends beyond dramatic outbursts to subtle shaping of stellar motions and interstellar conditions. By studying this quiet giant, astronomers gain a better understanding of the hidden engines that lie at the centers of galaxies throughout the cosmos. The movement of stars and gas in the Sombrero Galaxy provides a direct way to measure its mass and to trace how matter is distributed from the bright center out into the faint halo. Astronomers construct rotation curves by observing the Doppler shifts of spectral lines emitted by gas clouds or by the integrated light of stars. These curves plot orbital velocity against distance from the center. In a system where visible matter accounts for nearly all mass velocities, would rise near the center and then decline at larger radii following the law of gravitation. Instead, in the Sombrero Galaxy, as in many others, velocities remain high far into the outer disk, implying that large amounts of unseen matter are present. This unseen component is called dark matter, and its gravitational influence is essential to explain the observed motions. Near the central bulge, orbital velocities increase steeply, reflecting the concentration of mass there, including the influence of the central black hole. Within a few hundred light-years of the core, stars move at hundreds of kilometers per second. Beyond this inner zone in the disk and ring, velocities level off and remain nearly constant with distance. This flat rotation curve continues to tens of thousands of light-years from the center, far beyond the visible extent of the bright disk. The persistence of high velocities demonstrates that the Sombrero Galaxy possesses a massive dark matter halo extending well beyond what can be seen. The contribution of each component to the mass distribution can be separated. The bulge contains the majority of the luminous mass with hundreds of billions of stars. The disk contains a smaller but still significant stellar mass along with gas and dust. The halo, while faint in visible light, contributes through its population of globular clusters and scattered stars. Yet even when all luminous matter is included, the total falls short of explaining the high velocities observed at large radii. The dark matter halo must contain several times the mass of the visible components enveloping the galaxy in a vast invisible structure. The shape of the dark matter halo is inferred by studying not only rotation curves, but also the motions of globular clusters in the outer halo. These clusters orbit at large distances where the influence of the dark matter is strongest. Their velocities are consistent with a halo that is roughly spherical, extending perhaps hundreds of thousands of light-years. This halo provides the gravitational binding that holds the galaxy together and allows it to retain its extensive system of globular clusters. Without such a massive halo, many clusters would have escaped over cosmic time. Detailed studies of stellar kinematics in the bulge also shed light on the mass distribution. The velocity dispersion of stars measured by the broadening of absorption lines in their spectra indicates how randomly they move. This dispersion is high in the bulge, consistent with the large central mass, and supporting the estimate of a supermassive black hole. The bulge contributes not only luminosity, but also a substantial fraction of the galaxy's dynamical mass. Models combining bulge light profiles with stellar velocity data reproduce the inner part of the rotation curve, confirming that the bulge is the dominant luminous component. The disk, although thin and less massive than the bulge shows, ordered rotation around the center. The rotation of gas clouds traced by radio observations of hydrogen and carbon monoxide matches the stellar rotation, demonstrating that both components are influenced by the same underlying gravitational potential. The agreement between gas and stars adds confidence to the rotation curve measurements and to the conclusion that dark matter is required. The study of mass distribution in the Sombrero Galaxy has broader implications for understanding galaxy formation. The presence of a massive bulge-thin disk and extended dark matter halo shows that the galaxy assembled in stages with early rapid collapse, forming the bulge and halo, followed by the development of a disk stabilized by rotation. The rotation curve provides a snapshot of the balance between these components today. Comparing such curves across galaxies of different types reveals how common dark matter halos are and how they influence visible structures. The Sombrero Galaxy stands out as an example of a bulge-dominated system where dark matter is nevertheless essential to explain the dynamics. The measurement of dark matter halos remains indirect, relying entirely on gravitational effects. Alternative explanations for flat rotation curves such as modifications to gravitational laws have been proposed, but the consistency of dark matter models across many galaxies strengthens their acceptance. In the case of the Sombrero Galaxy, the agreement between rotation curves, cluster motions and mass-to-light ratio supports the standard interpretation. The exact nature of dark matter remains unknown, but its role in shaping galaxies is beyond dispute. The dynamics of the Sombrero Galaxy also provide insight into stability. The thinness of the disk combined with its coherent rotation suggests that it has avoided major disruptions for billions of years. A large merger would have thickened the disk and altered the rotation curve. Instead, the observed regularity indicates a relatively calm recent history consistent with the survival of the dust ring and ongoing star formation. The stable rotation pattern has allowed the galaxy to preserve its striking structure. Comparisons with the Milky Way again highlight differences and similarities. Both galaxies show flat rotation curves requiring dark matter halos. The Milky Way's rotation speed near the Sun is about 220 kilometers per second, while the Sombrero Galaxy's outer disk reaches similar or slightly higher speeds. The difference lies in the bulge, which is far more massive in the Sombrero Galaxy, raising inner velocities to higher values. These contrasts illustrate how variations in bulge size and disk mass can coexist with similar halo structures producing different appearances while following the same underlying dynamics. The study of galactic dynamics in the Sombrero Galaxy is ongoing, with new instruments offering higher precision. Large ground-based telescopes equipped with spectrographs can measure velocities of individual globular clusters and planetary nebulae in the halo. Space telescopes provide stable imaging for mapping stellar distributions. Radio arrays trace gas motion at high resolution. Each dataset adds to the picture of how mass is distributed, confirming the essential role of dark matter and refining estimates of total mass. The result of these efforts is a view of the Sombrero Galaxy as an immense, well-balanced system. Its bulge anchors the center with concentrated mass and random stellar motions. Its disk rotates in an orderly fashion, thin and stable. Its halo extends far outward, containing both ancient globular clusters and vast amounts of unseen dark matter. The dynamics tie all of these components together, explaining why the galaxy maintains its shape and how it has evolved over cosmic time. The flat rotation curve remains one of the clearest demonstrations of hidden mass, and the Sombrero Galaxy provides one of the most striking examples accessible to detailed observation. Determining the distance to the Sombrero Galaxy has been an essential step in understanding its physical properties, because without distance measurements, astronomers cannot convert observed angular sizes into true lengths or apparent brightness into intrinsic luminosities. Over the years, multiple independent techniques have been applied, each with strengths and limitations. Early estimates placed the galaxy at various distances, but as methods improved, a consensus value of roughly 30 million light-years emerged, with uncertainties narrowed by cross-checking results. One of the main approaches has been the method of surface brightness fluctuations. This technique relies on the fact that the bulge of the galaxy is composed of countless stars, each contributing to the total light. When an image of the bulge is taken at high resolution, small variations in brightness occur because of statistical differences in the number of stars within each resolution element. The amplitude of these fluctuations depends on distance. The farther away the galaxy, the smoother the light appears. By measuring the fluctuations and calibrating them with galaxies at known distances, astronomers estimate the distance to the Sombrero Galaxy with good precision. Another widely used method is the Tully-Fisher relation, which connects the rotation velocity of a spiral galaxy to its intrinsic luminosity. By measuring the width of the hydrogen emission line in the radio spectrum, astronomers determine the maximum rotation speed. This speed correlates with total luminosity, allowing distance to be inferred by comparing observed brightness with expected intrinsic brightness. The Sombrero Galaxy presents some complications since its classification as spiral or lenticular is debated, but the rotation curve is measurable and provides input to the relation. Distances derived in this way are consistent with those from surface brightness fluctuations, strengthening confidence in the results. Standard candles also play a role. In nearby galaxies, Cepheid variable stars and Type Ia supernovae serve as reliable distance markers. In the Sombrero Galaxy, individual Cepheids are too faint to be observed with current instruments, but supernovae have been detected in the past. These luminous explosions provide one-time distance estimates when carefully measured. The values obtained align with other methods, again supporting the distance scale. Globular clusters in the halo also contribute through their luminosity function. The brightest clusters have similar intrinsic brightness across galaxies, so by measuring their apparent magnitudes in the Sombrero Galaxy and comparing them with local calibrations, astronomers derive further estimates of distance. Each method carries uncertainties. Surface brightness fluctuations require assumptions about the stellar populations in the bulge. If the stars differ significantly from calibration, galaxies' results can shift. The Tully-Fisher relation depends on accurate classification and on the inclination of the galaxy, though the nearly edge-on view of the Sombrero Galaxy makes inclination straightforward to measure. Supernovae provide precise distances when observed, but they are rare and unpredictable. Globular cluster luminosity functions rely on large statistical samples, which in the case of the Sombrero Galaxy are fortunately abundant. By combining all these methods, uncertainties are reduced, and the true distance becomes clearer. The consensus value of around 30 million light-years places the Sombrero Galaxy well outside the local group, but still relatively near in cosmic terms. At this distance, its angular size in the sky translates into a physical diameter of about 50,000 light-years, smaller than the Milky Way, but massive because of its dense bulge and rich halo. The distance also allows calculation of its total luminosity, which is several times greater than that of the Milky Way. These values establish the Sombrero Galaxy as one of the most massive galaxies within the local volume accessible to detailed study. Determining distance is not merely a technical exercise. It underpins every physical property attributed to the galaxy. Mass estimates from rotation curves depend on distance, because velocities are measured in angular units, converted to linear scales. Luminosities depend directly on distance squared. Star formation rates inferred from fluxes of ultraviolet or infrared light require distance to translate into absolute values. Without reliable distance comparisons with other galaxies would be meaningless. The careful convergence of multiple methods in the case of the Sombrero Galaxy ensures that derived properties are trustworthy. Historical progress in measuring its distance reflects advances in astronomical techniques. In the early 20th century, distances to galaxies were poorly constrained, and estimates for the Sombrero Galaxy varied widely. The development of the Tully-Fisher relation in the 1970s provided one of the first reliable tools, though its application to a bulge-dominated galaxy introduced caution. The advent of space-based telescopes in the 1990s allowed surface brightness, fluctuation measurements with unprecedented precision. Supernova observations in the late 20th and early 21st centuries added further checks. Today, although small uncertainties remain, the range of estimates is narrow enough for astrophysical studies to proceed with confidence. Distance determination also connects to the broader cosmic distance ladder, the hierarchy of methods used to measure progressively greater distances in the universe. The Sombrero Galaxy occupies an intermediate rung, where techniques calibrated in nearby galaxies are applied to measure more distant systems. By verifying consistency among methods, astronomers ensure that the ladder is secure. The Sombrero Galaxy's agreement among surface brightness fluctuations, Tully-Fisher, relations supernovae and globular cluster luminosities provides an important validation point. Some ongoing research aims to refine the distance further by using planetary nebula luminosity functions. Planetary nebulae are shells of a gas expelled by dying stars, and their emission lines have predictable brightness distributions. By measuring many such nebulae in the Sombrero Galaxy, astronomers attempt to use this method as another independent check. Early results are promising and consistent with other techniques. The more cross-checks available, the more robust the distance becomes. With a reliable distance established, astronomers can place the Sombrero Galaxy in context within its environment. Its separation from the central Virgo cluster is confirmed by the distance measurement showing that it lies in the foreground rather than as a true member. This explains why it appears so prominent and well resolved despite not belonging to the main cluster. Its isolation also suggests that interactions with other large galaxies have been limited in recent times, consistent with the stability of its disk and ring. Thus, the distance to the Sombrero Galaxy is more than a number. It anchors every conclusion about size, mass, and luminosity. It validates comparisons with the Milky Way and with elliptical giants. It situates the galaxy within the local cosmic web, clarifying its relationship to the Virgo cluster. By applying multiple independent techniques and finding agreement, astronomers ensure that their understanding of this striking system rests on a solid foundation. The achievement demonstrates how careful measurement transforms a faint patch of light into a detailed physical object placed firmly within the three-dimensional universe. The present appearance of the Sombrero Galaxy is the result of a long history of formation and transformation. Astronomers attempt to reconstruct this history by combining evidence from its bulge disk halo and interstellar medium. The dominant bulge suggests an early era of rapid assembly when large numbers of stars formed in a short period of time. Such rapid star formation could have been triggered by mergers of smaller protogalactic fragments, or by the collapse of a massive gas cloud in the early universe. The result would have been a dense spheroidal component enriched by repeated cycles of stellar birth and death. The presence of many metal-rich stars in the bulge confirms that the region experienced multiple generations of star formation, each enriching the next with heavier elements. The immense size of the bulge indicates that this process was unusually intense compared with many other galaxies. After the bulge formed, the disk appears to have settled into a thin rotating structure. The coherence and thinness of the disk suggest that it has not been strongly disturbed for billions of years. If major mergers had occurred more recently, the disk would likely be thicker or more chaotic. Instead, the ordered rotation and narrow dust lane show that the system has remained stable. This stability implies that the galaxy has not experienced collisions with galaxies of similar size since the disk formed. Minor mergers, however, may have played a role. Smaller galaxies could have been absorbed into the halo, contributing globular clusters and streams of stars. Evidence for such accretion events may be preserved in faint structures around the galaxy. The abundance of globular clusters supports this idea, since many may have originated in captured systems. The dust and gas ring adds another clue. Its presence indicates that cold interstellar matter survived or was acquired long after the bulge formed. One possible explanation is that after the bulge assembled, residual gas settled into a disk where it cooled and formed stars. Another is that the galaxy accreted gas from its environment, or from minor mergers replenishing its disk. The fact that the ring is well ordered suggests that if such accretion occurred, it must have happened smoothly or long enough ago for the material to stabilize. The current modest star formation within the ring reflects this balance between supply and stability. The massive dark matter halo surrounding the galaxy must also be considered in its formation history. Dark matter dominated the early universe and guided the collapse of gas into galaxies. The richness of globular clusters and the high velocities observed in the rotation curve suggest that the Sombrero Galaxy resides in an exceptionally massive halo. This halo would have attracted large amounts of gas and small systems in the early universe, fueling the rapid growth of the bulge. It would also have provided the gravitational well to hold on to material and prevent disruption during minor encounters. The halo therefore forms the hidden framework around which the visible galaxy assembled. Another piece of evidence comes from the supermassive black hole at the center. Its enormous mass relative to the size of the galaxy implies that it grew rapidly alongside the bulge. The correlation between black hole mass and bulge velocity dispersion suggests a feedback process where energy released by accretion influenced star formation in the bulge. In the Sombrero Galaxy, the black hole's growth must have been significant during the early era of bulge formation, though it is quiet now. Its presence demonstrates that central black holes are integral to galaxy formation, rather than later additions. Astronomers model these processes using computer simulations of galaxy formation within the cosmic web of dark matter. In such simulations, massive halos form at the intersections of filaments, attracting gas that cools and collapses. Early mergers produce large bulges while continued accretion forms disks. Feedback from star formation and black hole activity regulates growth. The Sombrero Galaxy fits into this picture as a system where the early stages were especially intense, producing a bulge more massive than usual for its disk size, followed by a long period of relative calm that preserved a thin disk and ring. Minor accretions added to the halo but did not disrupt the structure. The result is a hybrid galaxy with both spiral and lenticular traits. The relative quiet of the past several billion years is suggested by the ordered disk and coherent dust lane. In galaxies that have undergone recent major mergers, disks are often warped or disturbed. The Sombrero Galaxy shows no such signs, implying that any strong interactions are ancient. The preservation of the dust ring also points to stability, since a recent violent encounter would have disrupted it. This quiet environment allowed the galaxy to maintain ongoing but moderate star formation while retaining its unique morphology. Uncertainties remain about the precise sequence of events. Some researchers argue that the bulge may have formed not only through early mergers but also through secular evolution, where material from the disk gradually migrated inward. However, the extraordinary size and richness of the bulge favour a rapid early formation. Others suggest that gas accretion from the intergalactic medium may have sustained the disk for longer than mergers alone could provide. The available evidence supports a combination of processes with early rapid assembly, followed by slower, steady accretion. The Sombrero Galaxy's formation history is therefore a story of contrast. The early universe saw intense activity that built a giant bulge and massive halo. Later times were quieter, with a thin disk and dust ring forming and surviving largely undisturbed. The present galaxy reflects both stages, showing the fossil record of ancient assembly, alongside signs of ongoing evolution. Each component, the bulge, the disk, the halo, the ring, the black hole, contributes evidence for this layered history. By piecing these clues together, astronomers reconstruct the pathways that produce this unusual system. In broader terms, the Sombrero Galaxy illustrates how galaxies need not follow simple categories or evolutionary tracks. Its combination of features shows that bulges, disks, halos, and rings can coexist in unexpected proportions. Studying its history deepens understanding of how galaxies grow in diverse environments across cosmic time. It stands as a reminder that the universe produces not only typical spirals and ellipticals, but also complex hybrids shaped by unique sequences of events. The Sombrero Galaxy does not exist in isolation. It inhabits a region of space near the constellation Virgo that is crowded with galaxies of many types, yet its exact membership within groups has been debated. It lies in the foreground of the Virgo cluster, one of the richest nearby clusters of galaxies, but measurements of distance show that it is not a true member of the cluster core. Instead, it resides several million light-years closer to Earth, likely belonging to a smaller group of galaxies or existing on the outskirts of larger structures. This position explains why it is so easily observed compared with cluster members that lie deeper within. Its proximity gives astronomers a clearer view of details such as the dust ring, globular clusters, and halo. Despite not being embedded in the Virgo cluster, the Sombrero Galaxy's environment still plays a role in its evolution. Galaxies often interact gravitationally with neighbours, and even minor encounters can affect their structures. Surveys of the region reveal a handful of smaller galaxies in the vicinity that may be satellites or loosely bound companions. These systems are much fainter than the Sombrero Galaxy and contribute little to its total mass, yet they may provide sources of gas or globular clusters through accretion. The presence of faint stellar streams around the galaxy hints at past interactions with such companions. These streams are difficult to detect, requiring deep imaging, but they provide evidence that material has been added to the halo over time. The absence of strong distortions in the disk and dust ring suggests that the Sombrero Galaxy has not experienced a recent major merger. In denser environments, galaxies often show tidal tails, warped disks, or asymmetric structures caused by close passages. The Sombrero Galaxy's symmetry indicates that it has avoided such disruptive events for billions of years. Its relative isolation may be the reason keeping it free from the violent interactions common in the core of the Virgo cluster. This isolation aligns with the idea that its disk and ring could survive for long periods without being destroyed by encounters. Gravitational influences from nearby structures, however, cannot be ruled out. The Virgo cluster exerts a general pull on galaxies in the region, and the Sombrero Galaxy may be slowly moving relative to the cluster. Its velocity relative to the cluster suggests that it is not gravitationally bound to the core, but still within its larger gravitational field. This context places the galaxy in the outskirts of a supercluster scale environment where tidal forces are weaker but not absent. Such forces may help explain faint distortions in the outer halo or the distribution of globular clusters. The study of the Sombrero Galaxy's environment also connects to the question of gas supply. Isolated galaxies can lose gas over time without replenishment, causing star formation to decline. In clusters, galaxies may be stripped of gas by the hot intracluster medium. The Sombrero Galaxy lying outside the dense cluster retains its dust and gas ring, suggesting that it has avoided strong stripping. Its smaller neighbours may have contributed gas through minor mergers, or the galaxy may have accreted material from the intergalactic medium. Either process would help sustain star formation at the modest rates observed today. Comparisons with other bulge-dominated galaxies in similar environments reveal patterns. Many lenticular galaxies and clusters are gas-poor and lack star formation. The Sombrero Galaxy differs by retaining its ring of cold gas and its active, though quiet, star-forming regions. Its environment may be less hostile, allowing these features to survive. The presence of nearby dwarf galaxies may also have provided material to refresh the disk. The richness of its globular cluster system may in part reflect such accretion, since clusters can be captured from smaller companions. Each satellite that merges leaves behind evidence in the halo, and the Sombrero Galaxy's halo is unusually rich and extended. The galaxy's position relative to the Virgo cluster also provides a useful perspective for astronomers. Because it is closer than the cluster, but in the same part of the sky, it serves as a foreground object that can be studied in detail without confusion from background systems. Deep surveys of the Virgo region include the Sombrero Galaxy as a prominent feature, but careful distance measurements separate it from true cluster members. This clarity allows it to be a benchmark for comparison. Observers can study its structure with confidence in its distance, while also comparing it with cluster galaxies to see how environment influences evolution. Although the Sombrero Galaxy does not dominate a rich group, its mass and luminosity make it the central object of its local environment. Smaller galaxies orbiting nearby would experience its gravitational pull and could eventually merge with it. Over cosmic time, such accretions may slowly increase its mass and alter its halo. The process is slow compared with the rapid assembly of its bulge billions of years ago, but it continues quietly. Each captured satellite adds to the complex history recorded in globular clusters and faint stellar streams. Environment therefore provides context, but not the full explanation of the Sombrero Galaxy's features. Its bulge size, dust ring, and black hole mass were established early, largely independent of present neighbours. Its current environment mainly influences whether these features persist or are disrupted. The relative calm of its surroundings has allowed it to maintain stability and to preserve structures that might have been destroyed in a more violent setting. This combination of early intensity and later quietness defines the character of the galaxy today. In the wider cosmic web, the Sombrero Galaxy occupies a node connected by filaments of galaxies and dark matter. Surveys mapping large-scale structure show that it lies on the edge of the Virgo supercluster part of the intricate network of galaxies that extends across hundreds of millions of light-years. Its location in this network may have influenced its early growth by channeling gas and smaller systems toward it. Today, those flows are weaker, but the history of accretion is preserved in its halo. The study of its environment therefore links small-scale features like globular clusters with large-scale patterns of cosmic structure. By situating the Sombrero Galaxy within its surroundings, astronomers complete the picture of its evolution. It is not only a striking individual system, but also a participant in the larger patterns of the universe. Its stability reflects the calm of its local group. Its richness reflects early accretion, guided by a massive halo, and its survival of dust and gas reflects avoidance of hostile cluster conditions. The Sombrero Galaxy is both a product of its intrinsic properties and of the environment in which it resides, and the combination of the two has created the distinctive system observed today. A useful way to understand the Sombrero Galaxy is to compare it with the Milky Way and with other nearby galaxies that share some of its traits. The Milky Way provides the closest benchmark because its structure is known in detail from within. Both galaxies possess bulges, disks, halos, and systems of globular clusters, yet the proportions and properties of these components differ sharply. The Milky Way's bulge is modest compared with its disk, extending only a few thousand light-years from the center. In contrast, the Sombrero Galaxy's bulge dominates its entire profile, rising prominently above the disk and containing the majority of the stellar mass. The Milky Way's disk hosts spiral arms filled with gas and dust, sustaining star formation at a rate of 1 to 2 solar masses per year. The Sombrero Galaxy, although forming stars at a comparable or slightly higher rate, concentrates that activity within a single dust and gas ring rather than across multiple arms. The globular cluster systems of the two galaxies also highlight differences. The Milky Way contains about 150 clusters, while the Sombrero Galaxy may host nearly 2,000. This order of magnitude difference indicates that the Sombrero is significantly more massive, particularly in its dark matter halo. Such a large halo is required to bind so many clusters in stable orbits. The Milky Way's halo extends far but is not as richly populated. This contrast underscores the hybrid nature of the Sombrero Galaxy, which combines a bulge more typical of an elliptical with a disk more typical of a spiral, all within an unusually massive halo. The central black holes of the two galaxies are also distinct. The Milky Way's black hole has a mass of about 4 million solar masses, measured from the orbits of stars near the center. The Sombrero Galaxy's black hole is estimated at several billion solar masses, hundreds of times larger. This difference reflects the correlation between bulge mass and black hole mass, since the Sombrero's bulge is far more massive. Despite its size, the Sombrero's black hole is currently faint, producing little activity, just as Sagittarius A in the Milky Way is quiescent. Both galaxies demonstrate that central black holes can be massive yet quiet, influencing dynamics, without producing luminous outbursts. When compared with other nearby bulge-dominated galaxies, the Sombrero Galaxy shows both similarities and differences. Lenticular galaxies such as NGC 3115 also display large bulges and thin disks with little star formation. However, many lenticulars are gas-poor and lack significant dust. The Sombrero Galaxy retains its ring of cold gas, and dust making it unusual among bulge-dominated systems. Elliptical galaxies of similar bulge size often contain even larger numbers of globular clusters, sometimes tens of thousands, but they lack disks and dust rings. The Sombrero sits between these extremes, sharing properties with both classes, but not fitting entirely into either. Comparisons with galaxies undergoing interactions also highlight the Sombrero Galaxy's relative calm. The Antennae galaxies, for example, are colliding spirals experiencing massive bursts of star formation. Their shapes are distorted and tidal tails stretch into space. The Sombrero Galaxy, in contrast, shows ordered symmetry and modest star formation. This difference demonstrates the role of environment galaxies in dense regions often interact violently, while isolated galaxies can remain stable. The Sombrero's survival of a coherent disk and dust ring over billions of years reflects its quieter setting on the edge of the Virgo supercluster. Another comparison is with the Andromeda Galaxy, the largest spiral in the local group. Andromeda has a massive bulge, though not as dominant as the Sombrero's, and a disk with prominent spiral arms. Its globular cluster system contains about 500 clusters more than the Milky Way, but still far fewer than the Sombrero. Andromeda's star formation rate is also higher, with widespread activity in its arms. The Sombrero Galaxy thus represents an extreme case of bulge dominance compared with Andromeda's more balanced structure. These differences show the range of evolutionary outcomes even among galaxies of similar total mass. Comparisons also extend to scaling relations across large samples of galaxies. The Tully-Fisher relation, which connects rotation speed with luminosity, places the Sombrero Galaxy at the luminous end for its rotation speed, reflecting the extra contribution of its bulge. The fundamental plane relation for elliptical galaxies, which connects surface brightness radius and velocity dispersion, also describes the Sombrero's bulge well. These placements reinforce the idea that it straddles multiple categories. Its bulge behaves like that of an elliptical, its disk rotates like that of a spiral, and its halo is more massive than expected for either alone. Differences in stellar populations provide another point of comparison. The Milky Way and Andromeda contain broad mixes of ages and metallicities with widespread young stars in their disks. The Sombrero Galaxy's bulge is dominated by old metal-rich stars, giving it a redder color overall. Its disk contains younger stars, but these are limited to the ring and contribute less to the galaxy's total light. This division highlights how the Sombrero Galaxy is visually brighter in the bulge and less in the disk, whereas in typical spirals the disk contributes much of the visible brightness. Studying such comparisons helps astronomers test models of galaxy evolution. The Sombrero Galaxy demonstrates that bulge-dominated systems can retain cold gas and sustain star formation, contradicting the assumption that all large bulges imply quenched galaxies. Its rich globular cluster system challenges simple scaling with disk size, showing that cluster numbers can be high, even in galaxies with small disks. Its massive black hole illustrates the tight link between bulge growth and black hole growth. Each of these lessons refines theoretical models and widens the recognized diversity of galactic forms. The contrasts also have practical implications for observation. Because the Sombrero Galaxy is seen, edge on its dust lane is obvious, whereas in the Milky Way, seen from inside, dust obscuration is complex and irregular. Observing the Sombrero Galaxy provides a clearer demonstration of how dust affects starlight in a disk. Likewise, its globular clusters are all viewed against the background sky, making them easier to catalogue than those in the Milky Way, which are scattered across the sky and often hidden behind dust. Thus, the Sombrero Galaxy serves not only as a scientific comparison, but also as a teaching tool, offering clearer views of processes that in the Milky Way are harder to disentangle. Through comparisons with the Milky Way, Andromeda, ellipticals, lenticulars, and interacting systems, the Sombrero Galaxy is placed within the full range of galactic diversity. It stands out for its bulge dominance, its extraordinary globular cluster population, its thin but active dust ring, and its massive dark matter halo. These traits mark it as an exceptional system, bridging categories and challenging definitions. By examining both similarities and differences, astronomers situate the Sombrero Galaxy as a key object for understanding how galaxies vary and evolve across the universe. To understand the Sombrero Galaxy fully, astronomers examine it across the entire electromagnetic spectrum, because each wavelength reveals features invisible to others. In optical light, the galaxy is dominated by the bright bulge and the striking dust lane that bisects it. This view highlights the contrast between stars and dust, but hides regions obscured by absorption. In near-infrared light, the dust becomes partly transparent, allowing stars embedded within the lane to be seen. Observations with the Spitzer Space Telescope and ground-based infrared instruments have shown that the bulge is even more dominant at these wavelengths, with the ring glowing faintly as dust grains warmed by starlight radiate heat. This confirms that the dust is cool but abundant, masking much of the disk in visible images while shining gently in infrared. Far infrared and submillimeter observations from telescopes such as Herschel extend this view by detecting the emission of very cold dust at temperatures of only a few tens of degrees above absolute zero. These data allow astronomers to estimate the total mass of dust and to trace the detailed structure of the ring. They show that the dust is clumpy rather than uniform, with dense regions corresponding to sites of star formation. Without such wavelengths, the coldest material would remain invisible. Submillimeter mapping also links dust with molecular gas, since both coexist in star-forming regions. In radio wavelengths, neutral hydrogen gas is detected through its characteristic 21 cm emission line. Large radio arrays map the distribution and velocity of this gas across the disk. The maps reveal that hydrogen is concentrated in the ring and rotates coherently around the bulge, matching the dynamics traced by stars. Molecular gas observed through carbon monoxide lines at millimeter wavelengths also follows this distribution. These observations are crucial for understanding the raw material of star formation. They confirm that although the Sombrero Galaxy is bulge-dominated, it retains a significant interstellar medium organized in a stable ring. X-ray observations add another perspective. The Chandra X-ray Observatory has imaged diffuse hot gas near the central regions, and a compact source at the nucleus associated with the supermassive black hole. The diffuse emission likely arises from gas heated by supernova explosions or by weak activity from the nucleus. Point sources scattered across the disk and halo correspond to binary star systems in which material falls onto compact objects such as neutron stars. These high-energy observations reveal the energetic processes hidden within the otherwise quiet appearance of the galaxy. Even though the nucleus is faint compared with quasars, its X-ray emission confirms that accretion is occurring at some level. Ultraviolet observations from instruments such as the Galaxy Evolution Explorer highlight regions of recent star formation. Young hot stars emit strongly in ultraviolet, and in the Sombrero Galaxy, these sources are concentrated in the ring. The ultraviolet view therefore emphasizes the contrast between the old bulge, which is dim at these wavelengths, and the active ring which glows brightly. This confirms that star formation is ongoing even in a bulge-dominated system. The ultraviolet data combined with infrared emission from heated dust provide a consistent picture of modest but real star-forming activity. The integration of these multi-wavelength data allows astronomers to construct a complete picture. Optical observations provide the overall structure infrared, and radio reveal the distribution of dust and gas. Ultraviolet shows where stars are forming, and X-rays expose the activity of the nucleus and the endpoints of stellar evolution. Each band compensates for the limitations of others, producing a coherent model of the galaxy. Without this full coverage, key aspects would be missed. The dust lane might appear as an absence of stars rather than as a reservoir of material. The bulge might seem even more overwhelming without recognition of hidden young stars, and the quiet nucleus might be overlooked without X-ray detection. The Sombrero Galaxy has therefore become a textbook case of how multi-wavelength astronomy reveals the complexity of galaxies. Its striking optical image draws attention, but the deeper understanding comes from connecting views across the spectrum. By examining it in every accessible wavelength, astronomers uncover its layered structure and ongoing processes. The combination of a bright bulge, a dusty ring, a rich globular cluster halo, a massive dark matter envelope, and a central black hole can only be understood when all observations are considered together. The methods used to study the Sombrero Galaxy also demonstrate technological progress. Optical telescopes on Earth provided the first sketches and photographs, but space-based observatories freed from atmospheric interference allowed sharper, deeper images. Infrared satellites such as Spitzer and Herschel extended sensitivity to cool dust, while radio arrays like the Very Large Array and Atacama Large Millimeter Array mapped gas at high resolution. X-ray telescopes such as Chandra and XMM Newton probed hot gas and nuclear activity, and ultraviolet instruments revealed young stars. The coordinated use of these tools shows how modern astronomy requires data from many facilities, each contributing unique information. The galaxy has also been a frequent target for calibration and demonstration because of its brightness and distinctive shape. Images from the Hubble Space Telescope have become iconic not only for their beauty, but also for their precision. These data are used to test photometric and spectroscopic methods, ensuring accuracy for studies of more distant galaxies. The Sombrero Galaxy thus plays a dual role as both an object of study and a standard reference. Its combination of bright bulge, sharp dust lane, and accessible distance makes it ideal for refining techniques that are then applied across the universe. Multi-wavelength studies further reveal the interplay between components. The correlation of ultraviolet and infrared emission shows how young stars heat surrounding dust, re-radiating energy at longer wavelengths. The alignment of radio gas maps with optical dust lanes confirms that obscuring features correspond to real concentrations of interstellar matter. The comparison of X-ray point sources with globular cluster locations shows how binary systems evolve within ancient stellar environments. Each cross-correlation enriches the understanding of physical processes within the galaxy. By bringing together observations across the spectrum, astronomers achieve a holistic view of the Sombrero Galaxy. The galaxy ceases to be a simple optical image and becomes instead a complex evolving system with interlocking parts. Its bright bulge reflects early history, its dust ring sustains current star formation, its halo preserves ancient clusters, and its nucleus continues to accrete at a low level. This layered picture would be impossible without multi-wavelength astronomy, which has transformed knowledge of galaxies from flat images into dynamic multi-component structures. Even after centuries of observation and decades of study with modern telescopes, the Sombrero Galaxy continues to hold uncertainties that drive ongoing research. One major question concerns the origin of its enormous bulge. The size and brightness of the bulge suggest rapid star formation early in the galaxy's history, but the exact mechanism is not settled. Some models propose that the bulge formed through a series of mergers of smaller protogalaxies in the early universe, each contributing stars and globular clusters to the growing spheroid. Others suggest that the bulge may have grown through secular processes where stars and gas in the disk gradually migrated inward over billions of years. The truth may involve both mechanisms, but the relative contributions remain uncertain. High-resolution simulations of galaxy formation continue to test these scenarios against the observed properties of the Sombrero Galaxy. Another open question involves the dust and gas ring. While it is clearly visible and well studied, its origin and stability are still debated. Did it form from leftover material after the bulge assembled, or was it accreted later from external sources such as smaller companion galaxies or intergalactic gas flows? The regularity of the ring suggests that it has existed for a long time, long enough to settle into a stable orbit. Yet its continued presence requires either a large initial supply of gas or ongoing replenishment. Understanding how such a ring can persist in a bulge-dominated system is essential for explaining how galaxies like the Sombrero maintain moderate star formation long after their initial assembly. The number and properties of globular clusters in the halo also raise questions. The Sombrero Galaxy system is unusually rich with nearly 2,000 clusters. Why this galaxy in particular hosts so many remains uncertain. The abundance may reflect the massive dark matter halo, but it could also indicate a history of accreting many smaller systems, each bringing its own clusters. If so, faint stellar streams should be detectable in the halo remnants of those accretions. Deep imaging has revealed some hints of such streams, but mapping them fully requires more sensitive surveys. Clarifying the origin of the clusters would provide insight into how galaxies grow through hierarchical assembly. The central black hole, though confirmed to be massive, also poses unresolved issues. Its current activity level is low, but it may have been brighter in the past. How much energy did it release during earlier epochs, and how did this affect the surrounding bulge and disk? Did outflows from the nucleus regulate star formation by heating or expelling gas, as models of feedback suggest? Traces of such events may be difficult to detect, especially if they occurred billions of years ago, but subtle clues in the distribution of gas and stars might remain. Future instruments capable of probing the central regions at higher resolution may uncover evidence of past activity. The dark matter halo is another area of uncertainty. While rotation curves and globular cluster motions confirm its presence and vast extent, the exact distribution of dark matter within the halo is unknown. Is it smoothly distributed in a spherical shape, or does it have substructure left over from past accretions? The answer affects models of galaxy formation and of the nature of dark matter itself. Observations of faint stellar streams and detailed velocity surveys may help to map the halo more precisely. Until then, the dark matter remains an invisible but essential component, whose properties are only partly understood. Even the classification of the Sombrero Galaxy remains open to discussion. Some catalogues list it as a spiral, others as a lenticular, and some as a hybrid. This reflects not only its unusual structure, but also the limitations of classification schemes that rely on visible features. Modern approaches attempt to describe galaxies with multiple parameters, rather than single labels, but the Sombrero Galaxy continues to challenge neat categories. Its combination of a massive bulge, thin disk, coherent dust ring, and extraordinary globular cluster system ensures that it defies easy placement. This ambiguity is itself a subject of study, demonstrating how galaxies may not always fit into simple types, but instead occupy transitional or mixed states. The rate of star formation in the ring also invites further investigation. While current observations suggest a modest but steady rate of a few solar masses per year, the long-term trend is uncertain. Has the rate been constant for billions of years, or has it fluctuated with episodes of higher activity? If fluctuations occurred, what triggered them? Interactions with small satellites, instabilities within the ring, or variations in gas supply? Answering these questions requires not only observations of the Sombrero Galaxy, but also comparisons with similar systems to see whether such behavior is typical or exceptional. Instruments planned for the future may help resolve these questions. The James Webb Space Telescope, with its infrared sensitivity, is capable of probing dust-obscured regions in unprecedented detail. It can reveal the structure of star-forming regions within the ring and measure the properties of the bulge with greater accuracy. Next-generation radio arrays will map the gas in finer resolution, showing how it moves and whether it is being accreted from outside. Extremely large telescopes on the ground will measure the motions of individual stars in the bulge and clusters in the halo, refining estimates of mass distribution. Each of these tools will contribute to a more complete understanding of the Sombrero Galaxy. For now, astronomers acknowledge both what is known and what remains uncertain. The Sombrero Galaxy is recognized as one of the most massive galaxies within its distance range, with a bulge that dominates its light, a disk that retains gas and dust, a halo, rich in globular clusters and a central black hole of several billion solar masses. Its distance of about 30 million light-years is well established, and its rotation curve confirms the presence of a vast dark matter halo. Yet the details of how these features formed and how they have evolved remain partly unresolved. The galaxy stands as a reminder that even nearby well-observed systems can harbour mysteries. Open questions are not signs of failure but of progress. They define the frontier of knowledge and guide future research. The Sombrero Galaxy illustrates this process clearly. Each observation has added a piece to the puzzle, but the picture is not complete. Astronomers continue to refine models, collect data, and compare with other galaxies to approach answers. The Sombrero Galaxy remains a laboratory where theories of galaxy formation, dark matter, black hole growth, and star formation can be tested. Its uncertainties ensure that it will continue to be studied not only as a striking object in the night sky, but also as a source of insight into the fundamental processes that shape galaxies across the universe.